Hello, we are Buckeye Vertical representing the Ohio State University. Let's take a look at this year's team. These three members will be performing our mission. Our competition team is composed of 7 members and is subdivided into 3 sections: avionics, structures, and software. Our developmental team consists of 4 members. We will now delve into our drone.
The SUAS competition rules and Buckeye Vertical's mission plan lay out several vehicle requirements for the UAV. The requirements are that the UAV must take off with a weight less than 55 pounds, including the deliverables, and that the UAV must be able to fly 5 miles with a full load without exceeding the max aero distance of 25 feet of set positions location determined by the waypoints. To save time, the team chose not to have a refuel stage, which sets the requirement that our drone should be able to fly at least 15 miles for the 10 required waypoints in under a 30-minute time span. With this in mind, we found that a flight speed of around 18 to 22 meters per second would be ideal and that our battery life should be around 40 minutes at cruising speeds. These parameters were found after taking into account payload drops and were used along with numbers like weight in the worst case scenario to calculate thresholds for motor prop configurations as shown later on in this video.
For detecting the vision targets, the team split up the problem into shape, color, and character detection. The ODLC loop starts with running inference on a frame using the shape color model. Once an object is detected using the shape color model, the classification is then verified with the set of possible vision targets. If it's not one of the 5 vision targets given, then it is nullified. If the object has not been nullified for 15 frames and the classification is not unique in the set of possible classes, then the character detection model is run on just the bounding box around the object. Parallelly, the team's custom-developed object localization algorithm is run to find the geolocation object, which is then used to update the vision target map. For both the shape, color, and character detection model, YOLO V8 was chosen over other alternatives due to its efficiency and accuracy. To develop an accurate and reliable shape color detection model, the team used domain randomization to simulate a diverse dataset of vision targets to generalize to the real world. To accomplish this, the team created diverse and realistic environments in Unity 3D. The model was trained on the synthetic data, then fine-tuned on the 128 real-world images that were captured during previous flight tests and miniature versions of the targets. The final model the team developed has a mean average precision of 0.8539. For the character detection model, a synthetic dataset was also generated using Pygame and the CAR75 dataset. This allowed the model to generalize to various fonts while still learning the task of localizing the character. The final model the team developed has a mean average precision of 0.9678. The team employed a sophisticated algorithm for precisely locating the position of a vision target in the 3-dimensional space relative to the camera. By capturing images of a known calibration pattern from various angles, the team was able to obtain intrinsic camera parameters and distortion coefficients, ensuring accurate image rectification. Subsequently, a direct linear transformation was applied to find the position of the target relative to the camera position. From 24 meters in the air, the team was able to get on average 5 centimeters of air in their localization. To run these object detection algorithms in real time, the team decided to employ a Jetson Orin AGX. This was chosen over various alternatives, including other Jetson models like the Jetson Xavier NX or Jetson TX2, as well as general-purpose CPUs like the Intel NUC products. While these alternatives offered respectful performance, they lacked the specialized hardware acceleration and computational power required to efficiently run large YOLO V8 models in real time. The Jetson Orin AGX stood out due to its exceptional specifications, notably its high-performance ARM-based CPU with up to 12 core hours and a powerful GPU with 2048 CUDA cores. The team chose to use the CE ZR10 as the camera system for this year's UAV. The ZR10 was the optimal choice for many reasons aligned with the competition requirements and compatibility with our Pixhawk 6X flight controller. The main feature was the 10 times optical zoom and the 2K image resolution, which ensures image quality remains clear even at high altitudes. The camera also came with an axis stabilization system, which ensures image quality is not affected by drone vibration or movement.
For the payload mechanism, the team was between two designs, a delayed parachute deployment system and a winch system. After analyzing 7 different requirements, the team concluded the delayed parachute would be more effective due to its speed of drop, weight saving, and comparable accuracy to the winch. The delayed parachute deployment system is a sensorless design. The parachute is initially packed tight into a capsule which also holds the bottle. A fishing line runs from the parachute to 2 spring-loaded lever arms. Excess fishing line is wrapped around a cylinder. The bottle then releases from the drone via a servo. The servo is actuated by the off-board computer once a corresponding ODLC target is found. The bottle then falls in freefall until the parachute is tugged out by the fishing line. Each lever arm conducts a tug. The first tug pulls the parachute out of the capsule, and the second expands the parachute completely. After the 2 tugs, the line falls off the drone. Initial testing to polish the system was conducted in a controlled indoor environment to determine perfect fishing line length, parachute diameter, spring tension, and capsule design. Once complete, the ideal fishing line length was 18 feet shorter than the drop height on a 36-inch diameter parachute. The system had a 100% success rate in a controlled environment, with the mechanism working 100% of the time and bottle landing within 5 feet of the target. When installed on our UAS system, the mechanism worked 100% of the time as well. However, depending on wind conditions, the bottle would land in various positions. After dropping 40 times, we had a 75% overall success rate, with the bottle on average landing 15 feet from the target.
To communicate with the drone, we chose to use the CE-HM30, which has the capability to transmit both video and telemetry on the 5100 to 5825 MHz bands. This telemetry unit has a range of 20 kilometers and is connected to the UART port on the Pixhawk 6X, while video feed is transmitted via RTSP to the Jetson. Although there is noticeable video latency from the drone, it is sufficient for our mission and is perfectly compatible with our camera. Our packet loss for telemetry in flight is 3 to 7%, with peaks at 30% at times due to video transmission. To connect with our transmitter, we use the Spectrum DSMX receiver. This receiver sends and receives data on the 2.4 GHz wave with a range of over 2 kilometers. This is helped because of its satellite radio transmission. The transmitter that we are using is the Radiomaster TX16S since it easily connects to the receiver and has a long range. The data type used for radio signals is ppm. Our packet loss in normal test flight varies from 1 to 5% with peaks around 7 to 8.
The structure of our drone is composed of 3 2x2 12-weave carbon fiber plates, sandwiched by aluminum standoffs. This was chosen due to its high strength/stiffness to weight ratio. 12-weave carbon fiber tubes were used for the arms to provide minimal deformation under load. The plates were manufactured via CNCs, and automated saws were used to cut the tubes to limit human error. The top plate was used as an electronic compartment for our drone, housing the Pixhawk 6X, Air 4 GPS, Jetson Orn, PDB to power avionic components, receiver, LiDAR system, telemetry, as well as battery to power the avionics. It was crucial to support this plate well to limit additional vibrations being picked up by the flight controller, so 3D printed carbon fiber infused PLA was used to support the plate. The arms were connected via aluminum mounts angled at 5 degrees. This angle was introduced to put our center of gravity below our center of thrust. This mitigated stability loss in forward flight, something we struggled with last year. Additionally, these components were double supported via 3D printed clamps to ensure minimal vibrations were recorded by the flight controller from these clamps. The quadcopter uses T-Motors P83 motors coupled with G30 by 10.5 inch props. This combination enables the vehicle to fly with 50 pounds of forward thrust at 36 miles per hour, which is well above the required speed to complete 15 miles in 20 minutes. The drone is powered by 4 6-cell 25,000 mAh batteries connected in a 12S 2P configuration. To select the best motor prop config, the team calculated performance metrics for many T-motor configurations. Motor propeller specifications along with UAV system dynamics were implemented in a MATLAB script which calculated performance metrics across simple missions. Assumptions were made for unknown variables such as fuselage mass, battery capacity, and over multiple iterations, the script would improve the assumptions until it converged to a solution. Among all the configurations tested, the selected configuration achieved the fastest mission times.
For the autopilot system, the team runs a C++ application on the Jetson that constantly sends a stream of positions to the Pixhawk through the Mavlink messaging protocol. The team uses a finite state machine where the drone state space includes the following: completing loop, scanning, flying to position, dropping, and loitering. During scanning, once a vision target is detected, the drone will fly to the calculated position and drop the payload. After the drop is completed, the drone continues with the scanning procedure to find the rest of the vision target coordinates. Once all the vision target locations are identified, their coordinates are stored in a map, where the key is a unique identifier representing the combination of vision targets, and the value is a list of coordinates corresponding to those vision targets.
The team conducted over 45 autonomous flight tests. Each test consisted of a manual takeoff and landing. Through all the tests, the team has attempted over 250 waypoints and successfully hit all 250, leading to an average miss error of 0%. For obstacle avoidance, a k-means clustering algorithm determines the relative position and size of obstacles at discrete time steps. Obstacle velocities are calculated by comparing the change in position across multiple time steps. The avoidance algorithm, called velocity obstacles, takes obstacle data as an input and outputs a maneuver. First, the algorithm uses obstacle data and tune parameters such as time horizon, distance horizon, and protected zone to determine the proper mode: restore, maintain, or avoid. If there is no risk of collision, the restore mode is selected, which restores control back to the mission planner. If there is a medium level of risk of collision, the maintain mode is selected, which outputs a maneuver equal to the aircraft's current heading and velocity. If a collision is imminent, the avoid mode is selected. In avoid mode, the algorithm uses system dynamics to calculate a discretized set of reachable velocities within a time step. The velocities which lead to collision within a specific time horizon are eliminated, forming the set of reachable avoidance velocities. From this set, the velocity closest to the current velocity is chosen to ensure collision is avoided and course deviation is minimized. The algorithm was first tested in a basic Python simulator, then tested in JMAVSim, a UAV simulator. Once the algorithm performed well in the sim, it was tested during a real flight of a backup aircraft by flying two aircrafts near each other. Finally, the algorithm was tested on Airbus 1 in the same manner. Testing indicated that the avoidance mode was always selected when necessary and maneuver performed well at low speeds. However, the avoidance maneuver was not optimal at high speeds due to the simplification of acceleration in the system dynamics. Two alternative flight vehicles were considered apart from the quadcopter: a hexacopter and a transition eVTOL. The transition eVTOL was initially the design we were leaning towards due to its ability to cruise at high speeds without drawing huge amounts of power. However, a lack of experience and the complexity of design and manufacturing drew the team away from the option. For the hexacopter, this design was heavily studied and tested last year and showed promise with high stability and redundancy in the motors, allowing for multiple failures. The design the team tested, however, proved to have structural related concerns, causing issues with the vibrations, and was inefficient delivering payloads when considering weight of payloads and power drawn from motors. The team ultimately decided to choose a quadcopter since it would be lighter, more stable, and smaller, allowing for easier transportation. Other aspects that stood out was its ease of manufacturing and payload efficiency. Another area where the team considered alternatives was the obstacle avoidance system. The team identified candidates being a depth camera, stereo camera, and a LiDAR. The LiDAR was chosen due to its wide FOV and high range. The range was important given the high speeds both our drone and other UAVs in the competition were traveling at. This was why both the depth camera and the stereo camera were excluded from consideration. The depth camera had an effective range of 5 to 10 meters, while the LiDAR had a range of 40 meters. Another design choice made was the number of LiDARs on the drone. We initially planned to have 2 LiDARs on the drone to maximize FOV, which would be especially effective at detecting obstacles approaching from the rear. However, due to weight concerns and complexity of integrating 2 LiDARs into our system, we decided to only keep the top-plate LiDAR, as forward-facing obstacles were expected to be a greater threat in the competition.
In the development process, a lot of safety concerns stemmed from manufacturing carbon fiber. Both layups and cutting carbon fiber have health risks associated with them. When making layups, masks and gloves were worn to prevent epoxy from sticking to the hands of manufacturing personnel and to prevent toxic fumes from being inhaled. Operating a drone, no matter the size, always compromises the safety of the team and others in the drone's flight vicinity. To combat this problem, We always notified others in the area of where we are flying and let them know to stay clear of the drone's flight path. Along with this, we make sure that we have a shunt plug on our system so that motors can be disconnected while the prop arc is obstructed. We also make sure that all competition team members are notified when the drone is armed and disarmed during flight.
The team was able to complete 2 full mission tests with an average score of 3 out of 5 payloads. These missions consisted of 2.5-mile laps. However, these missions were compromised due to excessive winds at the time of testing, leading to lower than expected results. Out of the 2 tests, one had 4 out of 5 payloads hit, and the other had 2 out of 5. With this data in mind, we expect to hit at least 3 out of 5 targets, possibly more depending on the weather. Since we didn't need any more hands-on for monitoring tasks while the drone was in autopilot, we received the maximum score on both attempts, with only 2 people involved in the operation of the drone. No manual takeover was required, and the team was able to complete all 5 laps in 26 and 27 minutes respectively. Throughout our second year in the SUAS competition, the team has learned and grown in many different aspects. This year, the team successfully designed, manufactured, and tested a quadcopter drone that can compete all specified competition requirements. For image detection, the team developed an object detection and localization system for the UAV, dividing the task into shape, color, and character detection. Using YOLO V8 for both models, they achieved a high accuracy through domain randomization for diverse dataset creation. The system, running on a Jetson or an AGX, accurately localized targets in 2D space using a sophisticated algorithm while employing the CZR-10 camera system for clear imaging and stabilization, meeting competition requirements. The payload system of the drone employs a vertical drop parachute system which utilizes a 2-arm spring-loaded lever system to ensure accurate, consistent deployment of the payloads. Throughout the design, verification, and testing, it was concluded that this deployment system can consistently and accurately drop water bottles on the designated target. For drone communication, we utilized the CHM30 for transmitting video and telemetry on the 1500 5825 MHz bands, with a 20 km range of telemetry and RTSP transmission to the Jetson for video. Despite noticeable video latency, it remains compatible with our camera. Additionally, we employed the Spectrum DSMX receiver operating at 2.4 GHz with the RadioMaster TX16's transmitter, using PPM data type and experiencing packet loss ranging from 1 to 5% during normal flight tests. The drone structure features carbon fiber plates and tubes for strength and minimal deformation, manufactured with CNC and automated saws to reduce errors. Electronics are housed on the top plate, supported by 3D printed carbon fiber infused PLA to minimize vibrations. Aluminum mounts angle the arms for stability, while T-motor, P80X motors, and G30 x 10.5-inch props provide ample thrust for the required speed selected through iterative MATLAB calculations optimizing performance metrics.